So it is 8:30. We can start. This week, we are going to cover sensors and actuators. It's mostly going to be theory this week. And next week, you will do a lab on connecting a couple sensors, a couple different actuators to the Arduino. So just a reminder that lab 0, which was the LED thing, is due this Friday. And one thing that I did notice, many of you are done with it, but a lot of you submitted individually. So just as a reminder, if you did work with someone, only submit one and add your partner to the Gradescope submission. So I don't have to double grade the same labs, is all. So if you submitted 2 individual ones, but you were working with a partner, make sure you just delete the double submission, keep one of them, add your partner to the one submission. And that's all about that. Any questions about that? Okay. So sensors and actuators. So to begin to cover sensors and actuators, we actually have to cover this analog to digital conversion and then also digital to analog conversion, because we live in an analog world, right? So all of our signals that we're processing, they're continuous, they're in the time domain, and they don't have these discrete values. But our computers, they work on discrete digital values, right? So all of our sensors are going to be taking in this analog data, and they need to be able to convert it to digital data. And then when we output it to the actuators, again, they are going to be working in the analog world. So a lot of the times our output needs to be analog, so we need to convert from digital to analog to outputs, and then from analog to digital in order to process on inputs. So here's our sensors. They're going to capture the physical stimulus and convert it into some electrical signal, right? And then actuators are going to create this physical stimulus given the electrical signals that you send to it. So some examples of sensors are maybe temperature sensors. And then in terms of actuators, you have pneumatic systems, infrared, like your TV remote outputting infrared, or RF. And then we have motors and things like that in terms of actuators. And like we talked about, we need this analog to digital and digital to analog conversion. So analog is going to generate a voltage or current difference that must be measured and processed. So like for a temperature sensor, usually it's a resistor, and then its resistance changes based on the temperature. So you have this like lookup table based on what is the voltage across the resistor, because it would change based on its resistance. That's the analog value that would then need to be converted into the digital domain. And then there are also just purely digital things like GPS. GPS is purely digital. So the key here between the analog to digital conversion is we have temperature, which is continuous, right? It's this smooth signal. And then in order for our Arduino or whatever our embedded platform is to understand that signal, it needs to be converted to discrete, right? And then for our actuator to then modify the environment, signal is then converted back to continuous again. So this is kind of like a setup of a typical embedded system. We have here our analog to digital converter. That is what our sensors input into. And then this is our, say, our, right, that's going to process that information from the sensor. And it can display some things, but if it wants to modify the environment, it's going to use this digital to analog converter. And that analog output goes into the actuator, which would then modify the environment. And because it's modified the environment, maybe the sensor is seeing something new. And we keep doing this loop, right? All right, so here is a little bit about the real world systems and that are using these ADCs, are analog to digital converters, and DACs are digital to analog converters. So you have this continuous waveform that we are trying to sample and get the value of in order to put it into our discrete system. So the way that we do it is we can't possibly have this smooth continuous curve in the discrete system, right? But we can sample it very fast, right? So we're going to sample it at these fixed time intervals with a sample and hold circuit. And I'll show you an example of what that looks like. But you're going to capture the value for a short period of time, and you're going to repeat doing that over and over and over. So you get this approximation of the continuous time curve. And then in order to output this same thing, we would need to use the digital to analog conversion. And again, we're in discrete, so we can't output to continuous. So it kind of becomes like for that set period of time, it's this one set value that approximates the curve. And then for the next step in time, it's the next value that it should be, but it just doesn't change during that time. And we keep doing that. So we get this approximation of the output as well. All right. So we talked about signal sampling. So sampling converts this continuous time signal into a discrete time signal because we are sampling it in discrete time intervals. And it's going to create this kind of approximation of the continuous time signal based on the sampling frequency. So the way that we are going to sample these signals is with an impulse. And we have a sample and hold circuit in order to capture the value at that time. So here is a sample signal. So ideally, our samples are instantaneous. So as fast as possible, so that we can capture that input at that time interval, as well as if we can make it faster, then maybe we can sample more frequently. And if we sample more frequently, we get a higher quality approximation of the signal. And this is what our sample and hold circuit looks like. So you sample by connecting the inputs, which is the signal that we want to sample, to this simple sample and hold circuit. it's going to charge this capacitor, which will then hold that value for that set amount of time. So that's our system can then read that value. So this is the simple sample and hold circuit. And here is a example of kind of something that we would maybe want to sample. So we have this strobe lights with 4 hertz, and it's illuminating a spot on a rotating disc. So if we sample it at 4 hertz, and the rotation of this disc is 1 hertz, then at time 0, we would see that it's at the top. At time 0.25, which is our next sample, right? We would see it on the right side at 0.5. We would see it at the bottom, 0.75. We'd see that at the left. And then time 0 occurs again because that is the full rotation. So we see that we don't actually see the full rotation of the strobe lights. We're only seeing these 1, 2, 3, 4 distinct positions of it. But from those positions, we can interpolate that it was rotating clockwise, right? So the question that we might want to ask is, how fast should we sample? And does it matter? So the example that we're going to use is this sine wave, right? So this is a sine wave, goes up and down, right? And let's say that if we sample once per cycle, right? If this is our sine wave, and we sample at like say the sine wave frequency is 1 hertz, and we're sampling at 1 hertz. Then every single time we sample, like here, we get the same value. So we might think that it's not a sine wave. What would we think that the input signal is? Yeah, just constant. So we need to sample a little bit faster, because if we have too low of a sampling frequency, we might mischaracterize our inputs, right? So we can, if we sample at 1.5 times per cycle, then we can think it's also a lower frequency than it actually is. So here we have a sample here, and here, and here, and here. And if we interpolate those, we would get a lower frequency sine wave than the real sine wave is shown. So there is some threshold that we need to pass in order to have the correct input waveform that we're sampling. So this threshold is twice the sample frequency. So our sample frequency needs to be at least twice the frequency of the inputs. And if we have that, then we can be confident that we are capturing the inputs properly. So here we can see that we are doing twice the frequency. So we have our samples at each of these points. And then if we just interpolate with even just straight lines, we can get a good approximation of this sine wave. So this sampling frequency is called the Nyquist rate, and it's for lossless digitization of these analog signals. So this is the Nyquist theorem. If our sampling frequency is Fs and our input frequency is Fin, then the criteria for a lossless input is our sampling frequency needs to be greater than or equal to 2 times the input frequency. If we have a sampling frequency less than 2 times the input frequency, that's going to result in that aliasing. So the aliasing would be that example of how we thought maybe the sine wave was a lower frequency than it really was. So that's what it's talking about here. Aliasing happens when the observed frequency is less than the actual one. So the frequency apparent, the frequency that we think from the sampling, is equal to the frequency of the inputs when the Nyquist criteria is satisfied. So that's it. Again, that criteria is our sampling frequency needs to be greater than or equal to 2 times the input frequency. And generally, we also go beyond this 2 times and perform oversampling. So here is our example. So again, back to the disk, if it rotates once per second and the light flashes 4 times per second, that means we get these 4 samples per rotation. So our sampling frequency is 4 times our input frequency, right? So we have satisfied the Nyquist theorem. So we can be relatively confident with this sampling that the frequency of the rotation of this disk is indeed once per second, right? But if we have the case that the disk actually rotates 5 times per second, and we're still sampling at 4 hertz, so 4 times per second, then we would still see these same samples, and we would think that the frequency of the disk rotation is 1 hertz, not 5 hertz. Because we're seeing these same exact samples, right, as before. So this is what we're calling aliasing. So if we wanted to make sure that we could capture this frequency correctly, what does our sampling rate need to be? Yeah, 10 hertz. At least 10 hertz. Okay. All right. So back to the analog to digital converters. So our analog signals are continuous, right? These are the things that we're trying to sample, right? And we're going to create this discrete version of the signal by doing the sampling. So this analog to digital conversion is going to map each sample onto a quantized range of voltages that can be represented by binary values. So this is our analog to digital conversion process. So we have the analog signal. We're going to sample it to create a discrete time continuous amplitude signal. And then we need to quantize it to then make it not only just discrete time, but also discrete amplitude signal. And then once we have this with mapping, we can create a binary sequence that our Arduino or whatever our digital system is can interpret. So here is an example of analog to digital conversion. Signal, I accidentally, that's okay. So our low voltage, the lowest it can be is 0. Our highest is 8. And then n is 3. That means that we have 3 bits to represent this analog to digital conversion. So if I have 3 bits, that means I have 2 to the 3. Different kind of steps that I can represent. These are the different combinations of my binary values. So that means that I can calculate this delta. I'm going to define as my sub-interval size. It's going to be V high, V low, divided by my number of combinations, right? So V high minus V low is number of combinations is, how many combinations can I get with 3 bits? 2 to the 3, which is 8. So my sub-interval size is 1 volt. Okay. So if I want to create these sub-intervals, I have 8 volts here, 0 volts here, 1 volt, 2 volts, 3 volts, 4 volts, 5 volts, 6 volts, 7 volts. Okay, I have these 8 intervals that I can represent. And then if we also want to think about this in terms of what is the error that I'm going to incur on this signal. So error is going to be, how should we define error? Going to be a difference of 2 things, right? So it's going to be the difference, say, of what is the real input minus the output of this ADC. Okay? And I'm going to take the opposite value. Because this ADC can only output 1 volt, 2 volt, 3 volt, 4 volt, 5 volt, 6 volt, 7 volts. Right? That's all it can do. It can't do anything in between. So there's always going to be this error. And this error, because we are stepping by 1 volt each time, is going to be bound. So the smallest it can be is 0, right? So if our input is exactly 1 volt, we can output 1 volt, right? But it's always going to be less than our sub-interval size, right? Because as soon as we reach this threshold, we are going to output the next step, right? So our error is bound by this equation, and that gives us this range, resolution, and accuracy. So our range is going to be the extremes that can be represented. So it depends on the inputs and our bit width. And the resolution is going to be determined by the number of bits, or the smallest difference that can be represented. And then our accuracy is how close the converted value is relative to the real value. And here is our quantization error, right? So based on our equation from before, we can only output these defined interval sizes, right? So in the example we had before, it was those 1 volt steps. But we can have this continuous signal. So that means that when we are exactly at the correct value, we have an error of 0. But then as we are creeping up the input into the next threshold, our error increases linearly. And then once we reach the next threshold, our error drops down all the way back to 0. Okay? And then it creates this little step function in terms of the error. And then we bound our inputs by the maximum and minimum value, so we know our error is going to stay in this range. So if we want to reduce the error for our analog to digital conversion, one simple way to do that is by what's the peak here defined by? Subinterval size, right? So how can we, based on our equation here, decrease our subinterval size? Yes. And we increase the number of combinations by increasing the number of bits. Right? So that would be defined by n. So the other thing I wanted to show was this. So there are other different ways to quantize signals. So what I showed you with the example and what will be on the homework that you'll be doing on Friday is this uniform quantization. But sometimes we know a little bit more about our input signal. Like if we say the distribution of our input signal looks like this, right? That would be a uniform distribution. Then linear quantization would be very good for them, right? But if our signal input distribution looks like a normal distribution, then that means that we have a lot more values that are going to be near 0 and a lot less near the edges. So in that case, we might want to use some non-uniform quantization so that we have better resolution towards the core part of our distribution of the input signal. And as we go out, our error increases. But it's okay because it's not very likely that we'll go very far out, right? So we're going to focus on this linear quantization, but just know that these other forms of quantization exist for the different kinds of input distributions. All right, so here is an example of an analog to digital converter. So this is a flash ADC. So it is a parallel design. And one of the advantages is that it is very fast because the conversion just takes 1 cycle. And the way that it does that is it creates this resistor network. And it is dividing up the reference voltage into these distinct ranges, right? With the resistors. And then it's doing this comparison with the input voltage. We have this voltage reference that we split up into the intervals, and then we have the input voltage. And then what each of these things are doing is a comparison between the reference voltage at the interval that it is handling. So this is handling the highest interval. And it's comparing that with the input voltage. And if the input voltage is higher, then this would be a 1. If it's lower, it would be a 0. So basically what this block is going to do is find which one of these bits is the highest bit. Okay? Because if that one is 1, all the ones below it are 1. And then based on that position of the highest bit that is a 1, it outputs the correct digital combination, the binary combination that represents that interval. So it does all 1, 2, 3, 4, 5, 6, 7 of these comparisons at once, and it gives the correct outputs. Okay? So it's very fast, but the disadvantage is it's a lot of components. So we need 2 to the n minus 1 comparators for an n bit AC. Here is a different design. This one is sequential. So the advantage is that it only has a few components, just has the one comparator, has this digital to analog converter and a counter. So it has 3 components rather than all of these different components. Okay? But the disadvantage is that it's very slow. So the way that this one works is this counter is going to loop through all of our possible combinations. And then based on the counter value, that's going to be input into this digital to analog converter. And it's going to output the value of the thresholds, one threshold at a time. So it's going to start at 0. Then if we go back to our other example, it would output 1, then 2, then 3 volts, then and so on. And it's just trying to figure out, okay, when is this input voltage finally less than the voltage that I'm giving here? And when that is the case, that means that it was the input voltage belongs to the previous threshold, right? So it just cycles through all of your different combinations and figures out which one is the correct one. So the disadvantage is that it's very slow, right? Like for our examples of 3 bits, it would take, if the input voltage is in that highest threshold, it would take 7 cycles to figure out that the input voltage needs the highest output. So that's in the worst case. It takes 2 to the n minus 1 cycles for this analog to digital conversion. But the advantage, it's very small, right? So we see how this one works. So this one is the last one that we'll cover. And this is, again, a sequential design, but we're going to go about it a little bit more cleverly. So rather than just starting from the bottom and then incrementing until we get to the top, this one is going to implement a binary search algorithm, and it's going to start from the middle. And then based on the comparator, if the input is greater than the middle interval, then we know that we only have to now search the upper half, right? So just in one cycle, we got rid of half of the possible values. And then what we do next is we go to the middle of the now upper half. And if again, the input voltage is higher, we've split our search space in half. And we keep splitting our search space in half until we get to one final interval. And that is what our input voltage will be mapped to. Right? So that's a lot better than this design that only checks one thing at a time. Okay? So this one splits our search space into half every single cycle, and it just needs a little bit of addition compared to the previous design. Okay? So this conversion is going to take n cycles in the worst case. Whereas this one takes 2 to the n. So exponentially more in the worst case. So this one is kind of the in-between design, right? It's very fast, but it's not as fast as the Flash ADC. And it has a little bit more components to it compared to the ramp ADC, but it is much faster than the ramp ADC. So this one is what is mostly used as ADC designs, unless you have very, very small bit width. If you have very, very small bit width and you're not can handle it, the Flash ADC is relatively small and would be the fastest. Yeah.
So again, using Flash or the successive.
For which one?
Do we use ACs in this class? We do. We're using the successive approximation.
So the Arduino does have ADCs in it, and the Arduino is using successive approximation ADC, but it's abstracted away from you. So I just am showing you this as the theory behind it so that you're aware of it, but you won't be like designing these things. You'll just be using them. You would be creating these things in a later course, like an EE course. I'm not sure which one it would be here. All right, so this is your question for today. And we'll end with this question. So if this is our setup, V low is 0, V high is 2, number of bits is 6, and V in is 1.65 volts, what is the output voltage of the ADC? Your code for today is 077. And remember the ADC outputs, basically the combination number that corresponds to the interval, like which number interval the inputs maps to. It does not output a voltage. Okay, so is anyone still thinking about this one? Good. Let's go over this one together then. And this is where we will end after today. On Wednesday, we'll go over digital to analog conversion. And then Friday will be time to work on examples of this. And that'll be your homework. Okay, so we have our voltage range of 0 to 2. So I can just calculate the resolution. So 2 minus 0, and we have 6 bits. So my number of combination is 2 to the 6, which is 64. So I have 2 over 64, which is 1 over 32. So this is my resolution. Then if I want to calculate the interval that this input belongs to, I can do this equation. So I have m is my interval number, 1 over 32. So m times 1 over 32 gives me what is the lower range of my inputs. And my inputs is 1.65. And then my upper range would be n plus 1, 1 over 32. So if we solve for this and get the range in terms of m, we can do that by just multiplying by 32, right? So multiply everything by 32. And that is 52.8 m plus 1. So in this case, m would be 52, right? So our inputs would be in the range of the 50 seconds to the 53rd interval. And we are quantizing it. So we can't output 52.8, but we can output 52. And remember, we don't go up to the next threshold until we pass it. Right? So that's why it's not 53. So basically 1.675 is the 50-second interval in the range 0 to 2 if it's split up into 64 different intervals, right? So that's all we calculated here. And just as a reminder, the key thing is we can't output the continuous value. It's this discrete value, and we always truncate. We don't go to the next one, even though 52.8 is closer to the next interval of 53, it belongs to 52. Right? So that is all for today. And the next class will cover digital to analog conversion on this same set of slides. Okay. Do make sure that you answer the poll.